Section 3.2 is going to pick up a little bit where we left off from we were talking about your exam, this idea of maximum and minimum values and slopes and tangents and so forth. So to start with, we're going to talk about something, a specific type of a maximum and minimum value, and that's called a relative or a local extrema. Those words are used interchangeably. Relative is the word that I'm most comfortable with using, I guess, because that's the word I've seen used the most. Local is fine as well. It just means in a small area or a local area to the others. If we have a point C, f of C, so just a point, xy, on an open interval, on which f of C is a maximum or minimum value, that is a relative extrema. Notice that the derivative at this point is either 0 or it doesn't exist. I'm going to draw you a couple of pictures so that you can see what this looks like. So let's say you had the whole graph and it looked something like this. I don't have any x's or y axes in, but it's not the point right now. This point right here is what you guys would have called a maximum value. But if you notice on the whole graph, there are values that are larger, right? And this is not the biggest y value on this whole graph. It is, however, the biggest y value locally. Okay? So that's what a relative or a local extreme value is. It's just that nearby, it is the biggest or the largest value. It doesn't have to, now notice on this particular one, these are slopes of 0, right? Because these have tangent lines that are horizontal. But we could actually do the same thing with a sharp turn. It could also be a relative maximum point. It's just the localized maximum. I always like to use this word, and maybe this is why I like this word relative, my family are quite short. People in my family are quite short. My mom is 5'2". Her mother was about 5'1". My sister's about 5'2". My aunt's about 5'3", and I'm 5'4". Unless I've shrunk, I guess, about 5'4". And my mother would tell you that she believes I'm tall. And I look at her and I shake my head. I mean, she's just convinced that I'm tall, right? When we were living in Ohio, we were youth pastors. My husband was a youth pastor at a church there, and every single one of our teenagers was taller than I was. Every single one. I mean, even the little 7th graders that we had were still taller than me. And so the whole point is that it's all relative, right? So when my mom says I'm tall, she's comparing me to all the short people in my family, right? But when you compare me to another audience, I might not be tall. So that's what this is. This is a relative or an argument that you're making in a local area, a small area surrounding the point, whether it is a peak or a valley. It's called a relative extrema. Now, these points are also called critical numbers. So the way that we find these points is we find locations where the derivative is either 0 or it doesn't exist. And if it's 0 or doesn't exist, then we have places that are potentially, anyway, relative extreme points. Now, they may not actually be extreme points. I gave this example just a moment ago. I'm going to write it in here. You can write it down if you'd like. If I have the function value x cubed, and I take its derivative, I get 3x squared. And 3x squared certainly does equal 0 in some places. In fact, it equals 0 when x is equal to 0. So this would be a critical point. It is a location where the derivative equals 0. However, we know based on the graph that it's actually not a relative extreme point. The graph looks like this. So the location that I'm talking about has in fact a slope of 0 here, but it isn't a relative extrema. Okay? The point that I just found is a critical point, which means it might be a relative extreme point. It's a testing point. So when we're finding these critical numbers, these critical places on the graph, we're finding sort of candidates. We're like seeking out all the candidates of things that might work, and then we're going to see if they do. Okay? There's several ways to see if they do. One way is to simply look at a graph and say, oh, yeah, that's not one of them. I can tell very quickly visually that's not one of them. Okay? We're going to do an example of one that actually does have some that work. So The directions are to find all the critical numbers by hand, which means we literally take derivatives, set things equal to 0. Or we might take derivatives and set denominators equal to 0, because that would be where we have things that don't exist. And then we determined if a critical number is a local max or a min or neither. Okay? And we're going to do it on this particular one simply by thinking about what the graph looks like. And the next problem we'll do it by actually graphing it on our calculator. Both are perfectly fine, legitimate ways to think about them. Sometimes you can use prior knowledge of what you know about graphs, and sometimes the functions are complicated and that doesn't work very well. So let's take a look at this one first. So if I'm finding a critical number, it means I'm finding a derivative and setting it equal to 0. So what is the derivative of x cubed minus 3x squared? Right, 3x squared minus 6x. Good. And then if I want to find a critical point, so that's just finding the derivative. A critical point is a location where this new derivative function either equals 0 or doesn't exist. Now, this exists everywhere, doesn't it? Why? Because it's a polynomial. So I don't have any doesn't exists on this one. But I can set this equal to 0 and solve that. So when I set this equal to 0, it is, like you said, a polynomial. And it's not linear, so I can't just move something to the other side and start dividing things out. What would I do instead? Right, I'd factor. I'd factor out, in this case, a 3x would be a good choice. So if I factor out 3x, what am I left with? Close, x minus 2. Right, because we actually took the 3 out. If we didn't take the 3 out, we'd be left with 3x minus 6 inside, which would be fine too. And then we would set each of those pieces equal to 0, right? All right, so what do we have? Well, we have x equals 0 and x equals 2. We have two critical values. They are critical values, flat out, for sure. The question then becomes, are they relative extrema? That is, are they locations where I have a relative maximum or relative minimum value? Well, this graph is an x cubed graph, right? I know it's got the minus 3x squared there. That's going to give it some of those peaks and valleys. That's what that's going to do for us, actually. But it's an x cubed graph. X cubed graphs either go down on the left and up on the right, right? They look like that. Or they go up on the left and down on the right. Those are our only options. They may have some peaks and valleys between, they may not, but those are the only two options. Which one is this one? Do you know? It's the top one. How can you tell? Because it's a positive on the x cubed. Because the x cubed is positive, it looks like that top graph. If that x cubed had been negative, like if it's a negative x cubed or negative 6x cubed or something like that, then it would have looked like my bottom graph. So this graph looks something like this one up here at the top. The other thing that we can know is because I actually have two locations right here, I'm going to have those peaks and valleys. They're going to exist, which means that my graph actually, if I fill it in from here, has to look something like this. That's the only way to connect those pieces and make it work. Does that make sense? So the first location right here would be a local max or relative max, and this location would be a local or a relative minimum. So what is x equals 0? Is it a max or a min? Which one is it? Is it the maximum or the minimum? Is it? Well, take a look at this. Let me erase this piece since we don't need it. In fact, I'm going to make this piece bigger too. I don't want that. I want it just to be bigger. We've agreed that it looks like this, right? Okay. These are my 2 points. One of them has an x value of 0 and the other one has an x value of 2. What is this one? Is this an x value of 0 or 2? 0. How come, Nathan? Yeah. It's just the number line issue here, so I don't know where the number line is. I'll just draw it down here. But there's two x values. 0 comes before 2, so the first one has to be an x value of 0. And the second one would have to be the x value of 2. So I actually have the x value of 0 as my maximum. And my x value of 2 is my minimum. Now this says critical numbers. If it actually used the word points, we would actually want to find the x and the y. So if x is equal to 0, how can I find what y is? Yeah, plug it into what? The original equation. Very good. So if I plugged x equals 0 into my original equation, that f of x equals x cubed minus 3x squared, what would the y value be? 0. So this doesn't ask us to do this on this one, but I want you to recognize how to do it because it's not difficult, and eventually we're going to be doing this on all the problems anyway. Now, what about x equals to 2? What is it? -4. I think that's right, yeah. So and you can actually look now at those y values and you could tell, right? This is a higher y value than this one, isn't it? So it also sort of makes sense that that first one at x equals 0 is a maximum because its y value is bigger than the minimum's y value. That doesn't even always happen. We'll see some examples about things that don't work like that too, but that's another indication. Let's take a look at another one. First part of the directions is the same. Find the critical numbers by hand. And then it says you can use a graphing technology, so your graphing calculator should be fine, to determine if the critical number represents a local max, min, or neither. So we'll graph it in a minute, but let's actually find those critical numbers by hand. This one's a little bit more complicated to find the critical numbers of because it's a quotient rule, you bet. So we'll get back to practicing on that. Some of you need some more practice, I know. All right, what is the quotient rule? What do I do? The bottom? Okay, what's the derivative of the top, Brooks?
2x.
Good. And then a minus, right? Okay, so what happens next? Someone else. Okay, and what's the derivative of the bottom?
1.
All right, and then I multiply that by what? The top. Good. And all of this is divided by x plus 2 squared. All right, so we're going to simplify that numerator. We're going to get 2x squared plus 4x minus x squared plus 2. I think we have one more simplification step of that denominator. I'm sorry, that numerator. What will that become?
Just the x squareds.
Combine the x squared. So I have x squared plus 4x plus 2. All right, so the whole point in doing this, oh, and I didn't write this is the derivative, excuse me, make sure you guys get that noted in there too. This is the derivative we just found. The whole point in finding the derivative is what? To find the slope, because what are we trying to find? Maximums and minimums. So what's my next step after I find this derivative? Right. So if the numerator was equal to 0, the whole thing would be equal to 0, and I'd have a horizontal tangent line, right? If the denominator was equal to 0, then I might have sort of one of these sharp turns or something, right? Now on this one I won't. What is the denominator equaling 0 going to do on this particular function? Make it what? It's going to make it not exist, but why? Graphically, what happens when that denominator is 0? What do I have? I have a vertical asymptote, right? It is a vertical line, it's an asymptote. I have an asymptote right there. I have a line that I'd get close to vertically and I can't touch. So there's not a maximum or minimum because it's an asymptote. So you're right in the fact that we're going to set that numerator equal to 0 and the denominator equal to 0. And the denominator is the easy one. So unfortunately, that's the one that we don't have any information that's helpful for. His is x equals 2 is actually an asymptote. So it's the numerator that we're going to have to work with. And that's not especially pretty on this one. Why not? What about this one's challenging? Yeah, it doesn't factor, does it? So we're going to have to use the quadratic formula. I know you guys know how to do that, but you have to recognize that that makes it a little bit different, and it's going to make the answers look less friendly. And they're going to have some square roots in them and so forth. So x equals negative b, which is 4, plus or minus the square root of b squared, so that's 4 squared, minus 4a is 1, c is 2, all over 2 times a, which is 1. All right, so the first piece is negative 4. What does the square root, everything underneath the square root, I'm not going to go into great detail, what does that simplify to?
8.
It is 8. Good. And this is all over 2. How does the square root of 8 simplify? 2 square roots of 2. I hope from an algebra class and or from Trig you remember how to simplify working with these. Because of the 4 here and the 2 outside of the radical here, I can simplify that with the 2 in the denominator. They all have a 2 in them. So they will all reduce and be divisible by 2, which leaves me with negative 2 plus or minus the square root of 2. So I do have 2 answers. In fact, I'll write them that way. Let me do that. I have negative 2 plus the square root of 2, and I have negative 2 minus the square root of 2. There are 2 answers here because of that plus or minus. So what we're going to do then is, well, let's actually make a notice at this first. Which one of these comes before the other one on the number line? Which one is on the left side of the number line, the other one on the right? Yeah, this one is and this one's on the right. Kind of just like what Nathan was looking at when we were doing the last one, right? They're just not as pretty numbers. All right, so take your calculator, and I'd like for you to graph this equation, the original one, f of x equals x squared minus 2 over x plus 2. You may need to, if your calculator is not set up to do something in math text, you may need to put the parentheses around that numerator and the parentheses around that denominator to make it work. And you're going to take a look at that. And I'm actually going to pause the video so that I can show it to you on the screen too. All right, so from the graph, what we saw is that this one right here on the left-hand side was actually a maximum, and that this one over here on the right-hand side was actually a minimum. Again, it doesn't ask us for the points. It asks us still for the critical numbers. So on this one, I'm not going to go through finding the y value because it would take a little bit longer than we're actually, and we're not actually asked to find it. But we could do that, right? We could plug those numbers back into the original function and find the corresponding output value. So my maximum, or my local max or relative max, is at x equals negative 2 minus the square root of 2. And the minimum, local or relative, is at x equals negative 2 plus the square root of 2. So this is my answer right here. And on the last one, I don't think I kind of marked that, but let me go back here and mark it for us here. The answer right here is that the maximum is at x equals 0, and the minimum was at x equals 2. That was my answer on that one. All right, so far so good? Okay, so this is sort of this relative idea, this idea of taking a local area and saying, what's the largest, what's the smallest value? We have another type of value called absolute extrema. Absolute extrema means exactly what it sounds like. It really is the largest, or it really is the smallest value. Now, the math notation for what we're talking about is we have a point, C, f of c, just an xy ordered pair, where f of c is less than or equal to f of x. Okay, that means it's smaller than all of the other surrounding values. Not just the surrounding values, but all of the other values, every other value. Well, if it's smaller than all of them, then it's a minimum. And likewise, on the second line, if the function value is greater than, it is larger than all of the other values, then it's a maximum. And your book gives this theorem a number. I'm not a big fan of numbering my theorems when they have names, so I kind of usually leave those out when that's the case. This is the extreme value theorem, or at least one version of it. It says that if you have a continuous function, because we've talked about continuous before, so it means it doesn't have things like holes, no jumps, okay? And it's closed and bounded, which means that it actually stops. Okay, there is a starting point and a stopping point, okay? And the fact that that's the bounded part. The fact that it is closed means that you actually have the location in, you can actually equal the endpoints. Okay, that's the starting and the stopping point as well. If that's the case, then there will always be an absolute maximum and an absolute minimum. Always. Now, they may occur at one of two places, okay? So where could they occur? Well, they could occur at relative extreme points, right? So like, let's pretend that we had the graph that looked just like this. It stopped here and it stopped here. So if you take a look right here, that relative maximum is the maximum on the graph. Okay? So that's one point, one possibility. However, if you'll notice the way that I've drawn the graph, in fact, I'll draw it just a slight bit different so that it'll have a one answer instead of multiple answers. If the graph were done like this, it does not have a relative minimum at all, does it? It doesn't have a valley. It doesn't have a sharp turn or anything to create a valley here on this graph. However, the two endpoints create another set of points that we can talk about. In this case, this first endpoint right here would be my absolute minimum value. It's simply the smallest y value on the graph, the portion of the graph that I'm looking at. Okay? So when we're looking at finding extrema, there are two types. I should say even finding absolute extrema. Sometimes you'll say it written that way. Absolute extrema. You either have relative extreme values, which are the critical points, or you have the endpoints. What that means is you actually have to test all of that. So if you're told to find the absolute extrema, you can't only test relative extrema, and you can't only test the endpoints. You have to test them all. All right, so let's take a look at one where we're going to do that. I chose the trig function here because I haven't done one with you today. Felt like you needed some trig in there. Find all absolute extrema of the given function on the indicated interval. So our function is a simple one. It's 3 cosine x. So the first thing we would do is we find critical points. So critical points are found by doing derivatives equal either to 0 or equal to things that don't exist, right? So what is the derivative of this function? -3 sine of x. Everybody good with that? Okay. Relative extrema means then I take the derivative and then what do I do with it? I set it equal to 0. Or doesn't exist, but this is a sine graph, which means it always exists, right? Like my polynomials, it's a nice one. All right, so where in the world is the sine graph equal to 0? Think about your unit circle. Where does the sine value equal 0? It might be worth noting that the -3 has no bearing on the conversation, right? Not 1. 0. Where else? It's at every pi value. At pi, and 2 pi, and 3 pi. Do you guys remember that unit circle? If you're looking at your unit circle, it's a terrible circle, but pretend. These are the two locations where the sine value is 0. Well, that's at 0, and then pi, and then 2 pi. And you go backwards too, right? You go 0, negative pi, negative 2 pi, and so forth. So it's all the whole pi values, okay? Now, not all of those values are really valuable to me right now because my interval restricts me to go from pi halves to 5 pi over 4. So which, if any, of these values are actually on my interval? Just pi. This is the only one that's in this interval. So it's the only one that I need to worry about. It is my only critical point on the indicated interval. So what do? Well, I indicated this before. What we're going to do is we're going to find out what is the ordered pair. That is, what is g of pi? So that is what is 3 cosine of pi. So what is 3 cosine of pi? It's actually -3. Okay, so we're over here And now we're talking about cosine values. Right, the cosine value over there is actually -1. So we actually get -3. Okay, so this ordered pair is one of my ordered pairs. It's pi -3. That is the xy ordered pair. This is a potential candidate. Right? This is one of my possibilities of a maximum or minimum value. There's two other possibilities. How do I find them?
Your endpoints.
Yep, the endpoints. See, the first thing we just did is we did the relative extreme of the critical points. The second thing we have to do is we have to test the endpoints. So what we're doing down here is we're testing points. We're actually finding what is the y value at these points. I've got these x values. I'm always going to use the two endpoints and anything that's occurring between that's a relative extrema. So I need to test the two endpoints still too. So we're going to find g of pi halves next. So what is g of pi halves? Well, let me move it up here. So I'm going to be finding 3 times the cosine of pi halves. All right, so what is that? Pi halves is up here on my circle. What's the cosine value up there? It's 0. So this is 0. So this ordered pair, this is ordered pair number 2, is pi halves, 0. Ordered pair number 3 will come from finding the other endpoint, 5 pi over 4. So we're going to do 3 cosine of 5 pi over 4. So what is the 5 pi over 4 is over here. What is the cosine value of 5 pi over 4? Good, negative square root 2 over 2. And then I've got the 3 that's times it in the beginning, right? So this is -3 square roots of 2 over 2. And the 3 is coming from right here. So this is my third ordered pair. So it's 5 pi over 4, and then -3 square root of 2 over 2. So I have 3 candidates for the competition for the competition absolute extrema. Yes?
How did you get the negative?
Because from here, in quadrant 2, cosine's negative. Remember, cosine's the x value of the ordered pair here, xy. And in quadrant 2, cosine is a negative value. It's a unit circle piece that we're using. Okay. If we were finding the sine value, it would actually have been positive at that particular point. Okay, so I've got 3 points squared in red. How do I decide from among those 3 points which is my maximum and which is my minimum? Okay, compare what? Of what?
Of the values we found.
Of which values we found?
G of pi, G of 5 pi over, yeah. 5 pi over.
Okay, the y values, right? Yeah, we're looking at the y values. So it's okay. These are the values we want to compare. I want to make sure that everybody understands what we're comparing. These are the 3 values because these 3 values tell you how positive, right, like how high or how low you go. So which of those 3 is the largest? 0 is actually the largest, isn't it? So this point right here is my absolute maximum. I'll rewrite these in a moment. Let me just jot them in here for now. Which of these 2 is the smallest? Is it the -3 or the -3 square root 2 over 2? It is the -3. I created the problem on purpose because I want you to recognize that you can't only test one thing. It's just as likely to be one of the relative points as it is to be one of the end points, and you have no way of knowing until you test both of them. So our answer is that our absolute maximum is pi halves 0. That doesn't look like a 0. And our absolute minimum point is pi negative 3. All right, I have one more example. It's really quick, so we have time to just barely squeeze it in. We're going to sketch a graph with some characteristics. I have 3 examples you're going to do in your homework, so this is one of those places where you have a little bit of flexibility. This one tells you you've got a function with a maximum value of 3 between negative 2 and 2, and that the absolute minimum doesn't exist. Notice, that's not a contradiction of that extreme value theorem, which said they always exist. It just doesn't exist between negative 2 and 2, right? This is not telling you that the value is between negative 2 and 2. They're telling you it doesn't exist for the whole graph. So a real quick picture of something like this would be this. There's other ways to do this, but I need it to go from negative 2 to 2. Those have to be marked for this to make any sense since it references it there. Somewhere between negative 2 and 2, I have to have a y value that is a maximum of 3. So I'm going to put it right here for no particular reason. But between negative 2 and 2, this is the biggest value it could be. And I could just make the graph then do this. Simple parabola is sufficient. Don't try and get crazy. Most of the ones that I'm giving you, you should be able to create something simple that does what you need it to do. This doesn't have an absolute minimum. It goes down forever, right? But it definitely has an absolute maximum, and it is occurring between negative 2 and 2, and it is at a height of 3. So it's very simple, it's very clean, and it satisfies all the conditions. Don't try to get crazier than it has to be. Okay? Any questions on that one? Okay.